Welcome. So this is part 3 of my series on flying fast missions with Copter. I suspect there'll be a few more parts to go as I discover issues and work around them. But for now, this is part 3. And if you remember from part 2, where I left it was I needed to use the position control XY feed forward to get to acceleration and velocity levels that I was looking for in the mission. So that was my goal, and that's what I achieved, and it was actually a lot of fun. A little bit dicey at times, but it was a lot of fun, and I've taken some video and I'm sort of pleased with the results. So what I'm going to do first is have a look at the test that I did to determine feed forward. And so let me switch myself and find the right graph, which is this one, I think. Yes. Okay. So slightly obscured by my video, but you can basically see. So what I've done is I've flown out a couple of 100 meters and then done an RTL mission. And what I'm going to look for is the position control. So I've done this roughly north-south, and what I'm going to look for is the position controller acceleration and velocity component in the north direction to determine their relationship, which is a proxy for the feed forward that I need. If I have a look at velocity, okay, it would help if I was actually in the right window. Okay, so here's the window. If I have a look at velocity, so here you can see the velocity, and you can see the velocity increases quite quickly in the north direction, then flattens out and then decreases again, and you see that my maximum velocity is about 25 meters per second, and I actually have this set to 30 meters a second. And then if I look at acceleration, and then you can see acceleration spikes and then flattens out as well. So let's just zoom in on this a little bit. So as predicted by Leonard, acceleration and velocity reach flat values, and it's the relationship between these two that gives the feed forward. Now, as my friend Justin said, this doesn't even survive GCSE physics, so I'm not quite sure why this is the case. Like, velocity should not be constant if acceleration is constant. Velocity should be increasing if acceleration is constant. And so I think this is probably something to do with the vertical component of the acceleration that the copter experiences due to gravity. So if you can imagine the copter's flying like this, gravity is in this direction, and the thrust is in this direction. And so with this thrust, sort of I need to get a writing, sort of a digital writing pad, so I can show this a bit more easily. But the thrust is in this direction, and that thrust component, which will create acceleration, that force will create acceleration. It has a component in the horizontal direction, and it has a component in the vertical direction. And the component in the vertical direction must match the acceleration due to gravity down. Otherwise, the copter will either shoot up into the sky or crash. So basically, these two must match in order for the copter to stay level. And so I think what we're seeing here with this constant acceleration is this component of the acceleration. So the constant acceleration, which is sort of the horizontal component of the thrust. And that's the way I got my head around it anyway. We're using a little GCSE physics. I'll see whether Leonard says that I'm correct, and I will sort of try and figure it out for myself. But needless to say, that the net is that you can read the values directly off the graph, which is great. Set up north-south, read acceleration, read velocity. And so if I have a look at these, and you can't see my window to show point values, but so this is the acceleration, and the acceleration is about minus 15 meters per second, and then the velocity is about minus 25.5 meters per second. So if I divide one by the other, get out my trusty reverse Polish calculator, 25.5, 15 divide, oops, sorry, other way around, 15 divided by 25.5, I get 0.59. And so 0.59 is the value that I'm going to use for position control feed forward. So this is the PSC, I think it's PSCXY. Just have a quick look, just to get the name right. So it is PSC underscore velxy underscore feed forward. No, FF, sorry. And so what I'm going to do is set that to 0.59 and then give it a try, see whether I get better acceleration. Because you remember the goal is to get up to acceleration, get up to maximum acceleration quickly and maximum velocity quickly without building up a lot of item. So I did that and I took some video. So let's have a look at the video. So we'll hide that one. And we shall start with this. Okay, I'm going to have another go at this. The videos hung and I got them in the wrong order, but so going to redo this. So first of all, here's the flight I did, just simple loiter and RTL with feed forward set.
Okay, the copter is in loiter. I don't know, hopefully you can see that. I'm going to hit RTL. This is with feed forward gain set, and we'll see what happens. Pretty awesome, really.
Which was pretty good. So, time for a mission.
Okay, I've set up a square mission, hopefully flying north, south, east, west, with the feed forward set and jerk increase. So hopefully this will go quite fast. I'm going to fly first FPV just in case anything goes wrong and I have to recover, and then if that goes successfully, then I'll fly without the goggles and take some video.
And I don't have audio set up on the FPV video, so I'm going to narrate while I play the mission. So this was the FPV view of the mission. And see, a little bit breezy. And what you'll notice also is the takeoff is reasonably rapid, but once we reach height, it then accelerates really pretty quickly. So you can see. Whoa. So the other interesting thing is this is not flying like an FPV pilot is. So the looking at the sky to turn is quite interesting, and the copter seems to make it all the way through. Okay. Reaches the last waypoint. You'll see that when I show you the graphs, I actually did the final waypoint in front of me just in case there was some problem. And you can also see vibration compensation coming on there because the copter was going really quite fast, and I'll sort of look into that in a little bit. So that was pretty good. I was pretty happy with that. So I thought I would try it again.
Well, that was successful, a little bit scary. So now try and take some video of it in action. You can see how things go.
Right, so here is the mission. Let's hope it doesn't hang this time.
Motors on.
Really need some very bright lights in the copter so you can see it at a distance.
You can see it's not very happy at all. That was quite scary.
So that went well, but it was a little bit scary. You can see that I wasn't expecting the sort of loss of control at the end there, and you can see the copter sort of swaying backwards and forwards until the EKF settles down. So worked well, went very fast, which was great, but clearly some control issues that I need to get to the bottom of. So let's switch therefore to the log of these two. So I've got a couple of logs here, and here is the first one. Okay, so first thing to notice is let me just find this one. Okay, so first thing to notice is you can see what I said here. I put the final waypoint, so waypoint 5, just in front of where I was sitting because I was a little bit concerned about the copter heading at 30 meters a second towards me. So that seemed fairly prudent, and given the experience, I think was a good thing to do. Now, the other thing to notice is, so, you know, tracing out fairly straight waypoints here, but then there's this fast, it overshoots and then gets back on the waypoint. And so I think one of the things I need to do is set a larger waypoint radius here. I think this is what the thing to, so the waypoint radius here is quite small, like 2 meters. So it's basically it's only when it's right on the waypoint that it starts to turn. So what I'm going to do when I next have some weather is set a larger waypoint radius so that once it hits the waypoint it starts to turn the corner. It's sort of a little bit more smoothly. So I don't know what I'll set that to. So I guess this is it comes around pretty quickly and pretty aggressively, but I think if I set the waypoint radius a little bit bigger, I won't get quite some of that aggression. Leonard also said that in the position controller there's you don't get a lot of control over the kind of angular acceleration here. I think it's sort of hard coded in the code. So one of the things he's going to do is provide a new setting that allows you to tune the, I think it's the angular acceleration. So basically the code is assuming that the copter has more thrust than it actually has to make this turn, and this is one of the reasons why it sort of overshoots and doesn't adhere to the waypoints quite so effectively. Yeah, so I look forward to that change. And the other thing to notice is you can see that it's sort of coming a bit more unstuck as it goes around. So first waypoint is pretty good. second waypoint, okay, third waypoint, seems a little bit off. And one of the things to look at, if we have a look at, so let's have a look at acceleration first and velocity. So back to the position controller logging, so in the north direction. So we've got north velocity and north acceleration. So let me just change the size here a little bit so see the graph a bit better. So first thing to notice is we get up to acceleration very quickly and we get up to velocity very quickly, which is nice. So let's just sort of dig into this a little bit. So this is, as you can see, accelerating very rapidly. So I've got jerk set quite high, so jerk is set to 4, so I've got 30 meters per second maximum velocity, 20 meters per second maximum acceleration, 40 meters per second maximum jerk, so that allows the acceleration to climb quite quickly. And you can see there's a little bit of, it reaches sort of maximum speed, 30 meters a second in the leg, which if you remember last time it wasn't able to do this. So when I last ran a mission, I wasn't able to get to maximum velocity in the leg. Still, it probably could accelerate a bit faster than this, but at least I'm getting to maximum velocity in the leg, and then as the acceleration then rapidly slows down as it comes to the corner. But the key point is what is I doing in the north direction? So if you remember last time, I was building up quite a lot in order to maintain the angle of the copter so that it would accelerate. So let's have a look at I here. So here is I. Mission planner not doing very well. Okay, so let's have another look. And so you can see that I is not so bad here. I'll show you in the other graph. It's a little bit more effective in the other graph. So, so I jumps up a little bit when the acceleration jumps up and then comes down again, but you don't get this massive hump that I was seeing last time. You do, however, get a massive hump on the downside, which is a little bit interesting. And I think if we look at this east-west, so let's have a look at the east-west component. Okay, so position controller east, velocity east, acceleration east, and then PID I in the easterly direction. Okay, so you can see that this is, so mission planners helpfully, we go to here, say, you can see this, so this is effectively this leg as it accelerates and deaccelerates into the leg, and then accelerates once more. You can see again I is creeping up here, so this seems like an I is creeping up a lot more than it was in the first leg. So it seems like the position controller is working well for the first leg, but then after the first leg things starting to unravel a little bit. All right, you can see the rest of the mission there. Okay, so if we switch back to, just for context, I'm going to switch back to the northerly velocity here, and what I want to do is look at what's going on in the EKF. And so if I look at EKF 4, which is, so these are variances of the different innovations, so square root of the variances, which basically means anything over 1, anything close to 1 is bad, anything over 1 is really bad because it stops using the sensor. So first of all, let's look at the position variance. And I'm going to do this side. And you can see actually the position variance is not too bad. The copter is roughly where it is supposed to be. 0.14 is much, much less than 1, so that's good. All right, so let's have a look at the height variance. And one of the things I noticed when the copter was flying around was it was definitely dropping in height as it got around the mission. So it started at 20 meters, but as it got further around the mission, it started to drop in height. So what does the height variance look like? Okay, so pretty bad here. Okay, so the height variance gets up to over 1, and this is all coming from the barometer. So you can see that. So here's, for reference, let's have a look, just zoom in here a little bit. So if you remember, this is the velocity in the north component, so this is the first leg, so everything's quite good in the first leg, and then what happens is we decelerate quite aggressively in the first leg, and the height variance spikes. And so, because we're using baro, the barometer for height, I think this is all to do with the prop wash and wind as the copter decelerates. And then you can see here it's accelerated. This is the end of this leg, and then accelerates into the next next leg here, which should be roughly flat, which kind of is. And you can see as it accelerates, the height variance gets even worse. So the EKF very unhappy, even more unhappy here. I mean, there was a little bit of wind, but yeah, very, very bad height variance. And so, and I think above 1, I think it stops using the, I want to say it stops using the barometer. Then relies on GPS. The GPS height is not very good either. So yeah, clearly I need to do something about this, because it's very, very unhappy in terms of the height. There was a suggestion of using the GPS when I looked at this log with Tridge. The GPS was equally unhappy. The GPS thought it was sort of 10 meters above where it was, and so if I'd used the GPS for height, the copter would have crashed into the ground. So I think baro is probably the safest option, but still not happy at all. Okay, so that's the height variance. And then let's have a look at the velocity variance. Okay, so the velocity variance also very, very unhappy. So velocity variance gets up to 1.3. So this is going to be, so velocity measured, I think, is a combination of GPS and inertial nav. So this will be quite badly affected by the vibrations in the copter, and also badly affected by GPS behaving poorly. Whether I can do anything about this, I'm not sure. I would think the GPS is probably more reliable in this case, but I'd have to have a look at that. So clearly, vibrations affecting the velocity variance quite considerably, and then finally the magnetometer variance. And again, so, okay, not quite hitting 1 here, but very, very high magnetometer variances. And you can see the 4 legs here effectively. So basically, every time you get rapid deceleration, rapid acceleration, the magnetometer variance shoots up. And so, although I've done a mag fit on the compass, what we think is going on here is that really I need per motor compensation rather than overall value, because the per motor compensation is probably, there's probably going to be a much higher, we'll have to have a look, but probably going to be a much higher variance around these very tight corners. And so there is support in the code for that. So what I'll probably try and do is dust off that support and yeah, see how it goes. So if I look at, so that's that graph. So it worked pretty well, but some challenges. And let me move on to the next guy. This final graph here. Okay, so not that one. This one. Yeah, okay. So this is the mission that went a bit, this is the mission I videoed. The last video I saw, this is where it went wrong a bit. So I think first off you can see that the, let's get this right here first. Oops. So I think first thing you can see is that the waypoint's getting progressively worse. So not too bad, not too bad, really quite bad, and then kind of all over the shop here. And you can also see that the throttle, so I've just graphed the throttle here. You can see that the throttle goes to maximum along these four legs, which is kind of what you want. You want maximum thrust if possible. So let's have another look at, let's just quickly show you what I showed last time. So velocity, acceleration, and I-term in the north direction. So here's the first leg. Okay, and this is great. This is exactly what we want to see. So you can see acceleration shoots up, velocity shoots up, I-term is basically constant. So this is a much better view from the feed forward component. But as you can see, as the copter goes around, this sort of level I-term starts getting more and more out of whack, and I suspect that's partly to do with the sort of the vibrations, but I also wonder slightly whether it's to do with the way that the thing is turning. And then you can see at the end here, this little bit here is just, it's really gone a bit mentally. You can see that the acceleration goes up and down, and the copter really doesn't know where it is. So let's see what this looks like from an EKF perspective. So I'll get rid of that. Let's have a look at the EKF again. Okay, so velocity variance. Oops. So velocity variance again quite high on these legs. Position variance again not too bad. Height variance again bad. So, and this is down to the barrow, and there's some code that copes with sort of wind estimation in copters, and I hope to use that because effectively you've got wind from the copter moving so quickly. So I hope to use that to enable the EKF to make better estimation of the barometer. And then the mag. The mag is very unhappy here, so you can see the mag is up to like 1.6, and this is probably partly to do, partly the reason for the loss of control. And I think that was all of them, wasn't it? So mag very bad here. So I think the only other thing to look at is the vibrations, just to see what this looks like. So first off, okay, Z vibrations quite high, X, Y. So not too bad, the vibrations. These are well within what you would say are reasonable for vibrations, and I don't think there's any clipping. So although there is vibrations, I suspect that the vibration compensation coming on is more a result of the height variance due to the barometer. So I really need to get to fix the barometer issues before making any further progress. Okay, so I had a lot of fun doing this, as you can see. Didn't lose any limbs, didn't lose any copters. Got some things to follow up on, in particular wind estimation for the EKF to improve the barometer performance, and per motor compass estimation to improve the magnetometer improvement. And yeah, I shall have a go with those, and then when I get some good weather, give it another go. But certainly getting up there in terms of getting to really fast missions, so I'm really pleased. Thanks for watching.